Good morning, lovely Year 11 students. I hope you are all well. I hope your families are well and safe. And so, welcome to another lesson. The title is Graph Transformations. As you can see on the screen, we have a bunch of information, some key information. Please make sure you continue to do your Sparks homework. Of course, I've been saying for a number of weeks now, the compulsory tasks are the bare minimum. On top of that, I would like you to do the XP boost tasks as well as the target tasks. It's really important for you to be exposed to a variety of questions, and so please make sure you try to do as much Sparks work as you can. Please do the practice exam paper if you have not done so already. Of course, catch up with overdue assignments if you have any which are overdue, and continue your recap. Stuff which we've done last year, stuff which we've done at the beginning of year 11, even stuff which you have done in year 9 and stuff. Just make sure you're constantly recapping. Of course, the main information for this week is that we have a test on Thursday, so please make sure you prepare yourself adequately for that test. I'm sure you're going to do well because I've been seeing some great work, but of course make sure you're recapping those remote learning assignments to ensure you perform well on Thursday's test. So, graph transformations. The starter is to draw the graphs y equals sine x, cos x, and tan x for the range 0 to 360. So when x is between 0 and 360. So pause this video now and have a go at the starter activity. Okay, so I remember at the beginning of last year, so maybe September, October time of year 10, we did trigonometry, and that's when I first showed you guys what these three functions look like. So hopefully you were able to sketch them correctly. Remember, the cosine graph starts at 1. That's how I always remember it. Cosine starts at 1. Sine starts at 0. So that's the big, I guess, one of the things which differentiates between cosine x and sine x. So we've already talked about one thing which is different. Their starting points are different. Cosine starts at 1. Always remember that. How are these graphs similar? Well, their shape looks quite similar, and they're both periodic functions. Now you might be thinking, what is a periodic function? So a periodic function is one whereby the graph repeats constantly. And so, for example, for cosine x, the period starts here at that 1, and you can see here, a period lasts for 360 degrees, and here our end point is, we're back to the point which we started with, and this will now continue, and I don't have much space, but this will now continue, and you will see kind of like continuous waves, if that makes sense. So if I drew it here, it would go like this, and it will keep on repeating, and each period will stay 360 degrees. If you look at sine x, the period is also 360 degrees, because here we start at 0 and we go, it increases, decreases, hits 0 again at 180 degrees, then it decreases to -1 at 270 degrees, and then it ends here, and then another cycle will start. We will see another repeat, another period of this sine graph. So always remember, they repeat every 360 degrees. Now moving on to a tan graph. Well, how is the graph of tan x different to sin x and cos x? Firstly, the shape looks different. It doesn't look like a wave as the sine and cosine graphs look like. It goes up, and then we have an asymptote, and then we have another, curve, and then we have another asymptote, and then we have a curve. So a tan graph is also periodic, and I'm actually going to show you on GeoGebra why it's periodic. Okay, so I said GeoGebra, I actually meant Desmos. So we've already looked at Desmos in previous lessons. As you can see here, it's periodic because this, I'm not sure what to call it, this curve, I was going to say N shape, but it's not really an N. This backwards S or sideways S curve is repeating, right? So we can see it here in the middle, but then here as well, you can see the same shape, and here it's constantly repeating. So going back to our PowerPoint document, we can see that the periods are every 180 degrees. Yeah, because from 90 to 270 degrees is 180 degrees. So every 180 degrees there will be an asymptote, and we will see this type of curve repeating itself. It says here, what is happening at these asymptotes? Well, there are no values on that line, right? So if I were to type tan 90 into a calculator, you should get a maths error come up. You could try doing that now as well. If you type in tan 270, you will get a maths error. It's similar to the reciprocal graph where 1 over 0, for example, if you type that into a calculator, you'd get error. It's the same principle. So yeah, whenever you see an asymptote, just know that there are no values on that line. No values exist. Okay, so with graph transformations, now the reason why I asked you to plot trigonometric functions is because we will be transforming them during this lesson, as well as some other graphs. For graph transformations, you need to have a good understanding of graphs. So what different linear graphs look like, what different quadratic, cubic, reciprocal, what all those different types of graphs look like, because we will be transforming them. Of course, transformations, you need to have a solid understanding of what they are, what a reflection is, what a transformations, what a reflection is, what a translation is, what a there's also stretches as well. And also you'd have to have a good understanding of functions, because you could transform graphs by using your understanding of functions and composite functions in particular, and we will look at some examples of where you can do that during this lesson. So yeah, moving on, I didn't want to speak about linear graphs because I think that you guys should know by now what it is, what y equals mx plus c is, and the same goes for quadratic functions, how they look like on a graph. So I'm going to briefly talk about cubic graphs, reciprocal graphs, and then move on to talk about exponential graphs as well. So we're going to start off with okay, so here's got a nice summary of what a cubic function looks like, what a reciprocal function looks like as well. So cubic graphs, draw graphs of the following on paper or using graphing software. You could use Desmos, for example. Compare your graphs. Can you identify key properties of the cubic graph? Now I know most of you will, just by looking at a cubic graph, just by looking at, a cubic function, you'd know what the shape of that function will be, or the shape of that graph will be. So me, by looking at this, I can see that the x cubed coefficient is positive, and so we will see an n shape on the graph. Okay, to be precise, it's going to be something like this, but sorry, something like that, because there are no roots. But yeah, I'm looking at this one, I can see that it will be the opposite. So it will be a reflection in the y-axis, and you can see on the previous slide as well, when A is negative, so let's start with positive. When A is positive, you will see an N shape, and when A is negative, so the coefficient of x cubed is negative, you will see what looks like a backwards N. So again, just looking at these other functions, I know whether it will be a normal N shape, so this will be a normal N shape. This will be a normal N shape as well. This is positive, so an N shape, but this one, although the first value is positive, the x cubed coefficient is negative, and so the shape of this graph will be a backwards N shape. So again, something we've talked about already, this is really important to the shape of a cubic graph, so just look out for that. Look to see whether it's positive or negative. It will be really important when you're sketching or plotting that graph. Moving on to reciprocal graphs, well, Emily, here it says Emily wants to work out some values to draw the graph of y equals 1 over x. So she's filled in the table, and then she's plotted her reciprocal graph. Now again, as you can see here, there is no value, and that's because 1 over 0 does not exist. So this, if you type that into a calculator, if you type in 1 divided by 0 into a calculator, an error will come up because it doesn't exist. So what that means is the whole line of x equals 0, so this line here, this dotted line here, is an asymptote. So, and actually, this line is also an asymptote here, because if you were to rearrange this, you get x equals 1 over y, and of course, 1 over y doesn't, well, y cannot be 0, because 1 over 0 doesn't exist, so we have two asymptotes, and as it says here, x equals 0, which is this one, is an asymptote, and y equals 0 is also another asymptote. Moving on to different reciprocal graphs. So if you are really curious, then please plot these on Desmos. I'm just gonna I guess sketch them very quickly because I want to focus on transformations today, but feel free to plot these on Desmos if you want to see what they actually exactly look like, or a more accurate representation of them. Here we have 2 over x, so it's roughly going to be something like this. Now, because of this negative sign, the graph of negative 3 over x would look something like this. So notice the two curves on the two other quadrants to the first one. And here we have 1 over x plus 2. So think about it. All our y values, we're adding 2 to all of our y values, right? We're adding 2 to all of our y values. So instead of the asymptote being here, it's going to be 2 spaces higher. So up here. And so our graph is going to look something like this. course this asymptote will still be here. And so this is y equals 2. This is x equals 0. So here what we've done is we've actually transformed the reciprocal graph 1, y equals 1 over x. So yeah, we'll look at more examples like this later on in today's lesson. Now we're going to talk about exponential graphs briefly. So again, if it is 2 to the x, then the shape is just increasing. So it's an increasing function. This is an example of compound growth. So sorry, compound growth can be modeled using this exponential function graph because it's increasing. For example, compound interest, the value in your bank account will increase over time. And so the graph would look something like this. Now, compound decay can be modeled using this graph because the value, as you can see, is decreasing and it never actually hits 0, but it does get very close. So as it says here, this is when there is a negative, so the x coefficient is negative, as you can see, 3 to the negative x. Here it says, will all exponential graphs pass through 0, 1? Explain your answer. Well, unless it's being transformed, then yes, because 2 to the 0 is 1. 3 to the negative 0 is also 1. So especially for these two examples, yes, it has to pass through 0. Other examples, if we say what's 9 to the 0, it's also 1. What is 21 to the 0, it's also 1. So anything to the power of 0 is 1. So yeah, exponential graphs will pass through 0, 1, unless of course they've been transformed. A common exponential growth example is the growth of bacteria. We start off with 1, then it becomes 3, then it becomes 3 squared, and then 3 cubed, and so on and so forth. We actually did a similar example, talked about a similar example during our compound growth lesson when I showed you the video of the footballers passing the ball. And so yeah, here it says, suppose at the start t equals 0, we have 1 bacteria. So alright, t equals 0, number of bacteria 1. After 1 minute, we have 3 bacteria. Oh yeah, it says that here, 3 every minute. After 2 minutes, 3 squared, which is 9. After 10 minutes, 3 to the 10. Now this is actually linked to what we're doing today, but it's useful to recap this. Yeah, you can work it out using a calculator. Exponential graphs, so I'm not going to talk about this too much, in too much depth, sorry, because again, we talked about exponential graphs in that same lesson I referred to a second ago. What happens is x increases, well, the graph is an increasing graph, so it just keeps increasing, and the rate of increase also is increasing as well. So the gradient is getting steeper and steeper the higher you get. Will y ever be equal to 0? No, it will not. Y equals 0 is an asymptote. And I mean, if we've already talked about the comparisons between y equals 2 to the x, y equals 3 to the x, and y equals 4 to the x. But again, if you like to look at them on the same set of axes, then please plot them on Desmos's graphing calculator. And here, this is something I refer to here as well. I'm not going to do it right now, but If you can't remember me doing this last lesson, then please do so. So you understand the relationships between these different exponential functions. So here it says, more exponential graphs, draw the graph of y equals 3 multiplied by 2 to the x. Compare it with y equals 2 to the x. Write down one thing they have in common and one thing which is different about them. So I'm actually going to plot these on Desmos. So here you can see a green curve which represents 2 to the x and a purple curve which represents 3 multiplied by 2 to the x. Now one thing I want to highlight is that 3 multiplied by 2 to the x is not the same as 6 to the x. And actually I'm going to type 6 to the x here just to show you that these two functions are different. So don't make that mistake of doing, okay, 3 multiplied by 2 is 6, so 3 multiplied by 2 to the x is the same as 6 to the x. We can see that they're not the same. 6 to the x, of course, goes through 0, 1, goes through the coordinates 0, 1, as you can see here, as does 2 to the x. And of course 6 to the x is going to be more steep than 2 to the x because 6 is higher than 2. And if we look at 3 multiplied by 2 to the x, it actually cuts the axes at 0, 3 rather than 0, 1. That's because 3 multiplied by 2 to the 0 is 3 multiplied by 1, which is 3, of course. Going back to our slides, here we have a bank account example, and what I'm going to do is sketch this on Desmos for you to see how the graph looks like. We're going to answer this question as well. So it says, actually let me read the whole question. Alana deposits £500 in a bank account which earns 4% compound interest per annum. Per annum means per year, by the way. Explain why the amount of money y in the account after t years can be given by this equation. Okay, because the initial amount is 500, so that's why the 500 is there. When t equals 0, y equals 500, and every year we are multiplying by 1.04. So yeah, that's why we have 1.04 to the power of t. Use a graph to estimate after how many years the money in the account will exceed 600. So in other words, when is y higher than 600? When is it first? Yeah, higher than 600. So 500 multiplied by 1.04t. Let's see how this looks like. 500 multiplied by 1.04 to the power of, I'll write x because this deals with x and y. So yeah, it's not coming up. You write y equals. Oh, sorry, I had to zoom out. Okay, so, and yeah, that makes sense, right? Because the initial amount is 500, so I'm not sure why I zoomed in on values between 1 to 5 or whatever it was. But anyways, as you can see, we have an exponential graph, and it's actually going to start at 500. And, okay, the scales on this are horrendous, but let's just see when it exceeds 600. So this point here, So with our graphing calculator, we just have to keep doing trial and error, subbing in different t-values to see when it would exceed 600. But as we can see here, okay, 4.6. So after 4.6 years, so it's safe to say after four full years, so at the start of the 5th year, we'll have more than £600 in our bank account. Coming back to the slides, we have another exponential for you to look at. Again, you could plot this on a graph. I'm not going to do it again because it's going to get repetitive, but please do so if you want to further understand how these contextualized exponential problems can be modeled on a graph, graphing calculator. Now moving on to functions. So we've talked about graphs. We are going to talk about transformations. Now we're going to talk about functions. Just recap what a function actually is. So a function is something which provides a rule on how to map inputs to outputs. So here our input is x. We put it in our function machine and the output is 2x. So for example, our input, let's say, is the value 3. We put it in our function machine and our output is going to be 2 multiplied by 3 because the rule is 2x. So for this specific value, our output will be 6. Let f be a function where fx equals x squared plus 1. So have a go answering these questions. They are quite simple. So yeah, pause the video. You could even do it in your head, to be fair. So yeah, pause the video and I'll go through the answers in a sec. So when x equals 3, 3 squared plus 1 equals 10. Here you have to be careful not to make a mistake because negative 2 squared is 4, not negative 4. 4 plus 1 is 5. Here, this is an interesting one. So x, composite functions, of course. So you sub this to x instead of this x, and so it's 2x squared plus 1. You get 4x squared plus 1. Here you have to sub in x plus 1 instead of this x. So it's going to be x plus 1 squared plus 1. If you think that you've struggled on a number of these, composite functions. I'm hoping that this was okay for you guys, but yeah, if not, then yeah, just recap composite functions. Please feel free to ask me questions as well. So now moving on to transformations of functions. So suppose that we have a function f of x equals x squared. Sketch this function. So of course you know how it looks like, a standard quadratic function. Then we are going to transform it. So f of x plus 2, again using your knowledge of composite functions, you will substitute this x plus 2 into this x. So it's going to be x plus 2 squared. Now, how do we sketch this? Well, y equals x plus 2 squared is a quadratic function which has repeated roots at x equals negative 2, right? Because x plus 2, so the root's always going to be the opposite. So here we can see the roots. Well, it's one repeated root at x equals negative 2. What do you notice about the relationship between the graphs of y equals f of x and y equals f of x plus 2? Well, the shape is the exact same. This graph has just been shifted 2 spaces to the left. So as it says here, the graph / line has translated 2 units to the left. So let's look at this. F of x plus 2, and it shifted 2 spaces to the left. So just think about that for a sec. Here I'm going to show you a few similar examples, but using the tables, and hopefully they'll be easier to understand. So on the same set of axes as f of x equals x squared, draw the following graphs. Y equals f of x plus 1, y equals f of x take away 2, and y equals f of x plus 4. So firstly, using my knowledge of composite functions, I'm going to write what these functions are going to be. So x plus 1 squared, x take away 2 squared, x plus 4 squared. So here we can see these 4 functions all being plotted on the same set of axes. So here we have x squared, which of course goes through 0, 0. X plus 1 squared will have its repeated root at x equals -1. So it's been shifted 1 place to the left. So plus 1 means a shift of 1 place to the left. So translation, 1 unit to the left. X take away 2 squared, so the repeated root will be at x equals 2, of course. And so when we see that negative sign, so x take away 2, the quadratic graph is being shifted 2 places to the right. And x take away 4 squared, it will be shifted, the x squared will be shifted 4 spaces to the right, because x take away 4 squared, of course, means the root will be at 4, x equals 4. So going back to our slides, here we can see a table of values, and of course that will correspond to the graphs. It says here, predict what the graph of y equals f of x plus 6 will look like. Test your prediction using graphing software. So remember we said when it's plus, so when it's x plus a number, we are shifting it to the left. And when it is x take away a value, then we are shifting it to the right. So if we have x plus 6, f of x plus 6, then that means we will shift our graph to the left. So we'll look something like this. So let me just change the color. If this is x squared, then f of x plus 6 will be something like this, where this is -6. Some more translations to look at. So the graph below shows y equals g of x. Use this to sketch the graph of y equals g of x plus 3 and g of x take away 2. So earlier we said if it's, for example, g of x plus a value, let's just say a, then you shift to the left. If it is g of, I'm not sure why that's happening, g of x take away, what's going on? G of x take away a, then we shift to the right by a units. And of course this is by a as well. So g of x plus 3, well, this point here will have to be moved 3 places to the right. So 1, 2, 3. Have to end up at -8, so it's not on the graph, but it looks something like that. We have to be very careful to make sure our gradient remains the same, because We don't want to squish the graph, change the gradient, we just want to move it left and right. So in this case, we're moving it left. Here we have a 1, so let's move that 3 places to the left. So 1, 2, 3. So our graph of y equals gx plus 3. Now using a different color, let's do this one. So negative 2, so we have to move it 2 spaces to the right. So this point will be shifted to here, this point will be shifted to here, this point will be shifted to this point. So let's again make sure the shape is exactly the same. We maintain this V shape, which has a gradient, which has gradients -1 and 1. So this will go something like this. Let's label it as well. Y equals g of x, take away 2. Describing a translation. So the red graph below has equation y equals h of x. So this one is y equals h of x. Give the equations of the red and green graphs in terms of h of x. Okay, so firstly, it's good to see that they've all been shifted left and right. They haven't been shifted up and down. We haven't learned about that yet. So we can only answer the questions for graphs which have been shifted left and right. So we know that I'm going to pick a point. I'm going to pick this point here. I can see that this has been shifted 4 spaces to get that blue graph. So yeah, just spotted this is a typo, that should be blue. Sorry about that pause. Yeah, so this should be y equals hx. Remember, shifting to the right, -2, because this is 0 and this is 2. I was about to write a 4 there, but I looked at the axes. Don't make these silly mistakes. I looked at the axes and I saw that these are actually 2 spaces. So 1 space, 2 space. X take away 2. And now let's label the green one. So the green one, okay, let's just use this point again. This one here, 1 point here, so that's going to be -1. So it's shifted 1 place to the left, so we have x plus 1 within the brackets. So I'll just underline these two. In terms of describing them, we've given the equations. You could also say that the blue graph has been translated by the vector, then you write the vector, which is 2, 0. So we can say the green graph has been translated by the vector -2, 0, because it hasn't gone up or down and it's gone 2 spaces to the left. So we're going to come back to this idea of our f of x being x squared, because now we will talk about translations where we're adding values like we're adding values and taking away values to transform the function. However, the values are outside the brackets. So remember earlier we looked at examples like f of x plus 1, where it's within the brackets, f of x take away 2, again within the brackets. Now you can see these values, the operations are clearly outside the brackets. So we're going to use this table. Here we can see the table being filled out. So for our different x values, if you square them, you get the corresponding f of x values. Adding 1 to each, so 4 plus 1 gives you 5, 1 plus 1, 0 plus 1, 1 plus 1, and 4 plus 1. These values, so 1 to equal 2 is negative 1, 0 to equal 2 is of course negative 2, 1 to equal 2 is, this is a mistake, and 4 to equal 2 is 2. So each time the x coordinate stays the same, but the y coordinate changes. Predict what the graph of y equals f of x plus 5 will look like. So I'm going to plot these on Desmos. Before I do so, just write what each function is. So f of x is x squared, of course. F of x plus 1 is just simply x squared plus 1. F of x take away 2 is x squared take away 2. And this function here, well, I guess the whole thing is going to be y equals x squared plus 5. So now I'll now plot these 4 functions on the same set of axes on Desmos. As it said on the slides, the x values don't change at all. The y values are changing. Same way on the previous set of equations we looked at, the y values didn't change and the x values were changing. Here, the y values are the only values which are changing. So the blue graph is of course x squared. X squared plus 1, what is happening here? So we're just adding 1. So 0, 0 becomes 0, 1. The x value doesn't change, but the y value, we're adding 1 to it. X squared take away 2 is the purple graph, and the x value won't change. Trying to isolate this. Oh, wow. Okay, the x value doesn't change, but the y value, we're taking away 2. So we go from 0 to negative 2. The red graph, the x value again won't change. None of the x values are changing. However, the y value changes, and we go from 0, 0 to 0, 5, because we're adding 5. The graph below shows y equals h of x. Use this to sketch the graph of h of x plus 1 and h of x take away 2. So I'm going to pick, which point should I pick? I'll pick this point. I can see this is 3, this is 2. So one place equates to 2 square jumps, if that makes sense. So h of x plus 1, this point will be here. Again, the x value won't change, but the y value is going to increase by 1. And so this will be here, this will be here. We could look at this one here and say it's going to be here. This is going to be here. So it's going to look something like this. Of course, it's not going to be a perfect drawing, but as long as you're roughly there, then you should get the marks in an exam. So this is this one. Let's change the color. H of x take away 2. So this value is going to be here. It's 3 take away 2 is 1. This value here is going to be here. This value is going to be here. So you have something like this going on. Here. Again, remember, x values are not changing, the y values are increasing by 1 or decreasing by 2. Describing a translation, the blue graph below has equation y equals g of x. So this is y equals g of x. Give the equations of a red and green graphs in terms of g of x. So let's just focus on this point. Describing translations are quite, I'd say, easy, because you just focus on one point. You see what is happening to it. So we go from 2 to 0. The y coordinate goes from 2 to 0. And so this is going to be y equals g of x. Make sure it's not within the brackets. Right, -2. Again, let's come back to this point here. It's 0, 2. This point here is 0, -4. So for the green graph, we've gone down 2, 4, 6 places. So alright, y equals g of x. Take away 6. We've gone down 6 spaces. In terms of describing it, you could also say this is a translation, and then write the vector, which is, again, no change to the x coordinate, but the y value is decreasing by 6. Likewise, the other one, translation 0, -2. So here we have our generalizations. Our original is, of course, y equals f of x. The first example I looked at was when the value is within the brackets. So that's going to be a translation with vector -a. Remember, when it's a plus, you're moving to the left. And when it's a negative, so when a is negative, then you're going to be moving to the right. Bear in mind here, the y coordinate is the same. So right, y same, x moves, I'll say, or transforms or translates, whatever you want to say. And here, y moves, and x is the same. And it does make sense as well. If you look at any function, if you add a to it, it will affect the y value. It doesn't actually affect the x value, because look, the x is the same. And again, just by doing practice, this will become second nature to you. As you can see here, we have two reflections, which we will talk about over the coming slides. Okay, before we do that, if a change is inside the brackets, it affects the x-axis. If a change is outside the brackets, it affects the y-axis. What we expect, or opposite, what we expect. So just to explain to you what this is, if we have f of x plus 3, I mean, naturally we'd expect it to shift to the right, because we're adding 3, we're expecting the x value maybe to increase by 3, and that's why our opposite, because we're not shifting to the right. X is not increasing by 3. The x value is actually decreasing by 3. So that is why you need to be very careful here. X is decreasing by 3. In other words, x is being translated with the vector -3, 0. That's why you need to be very careful, especially with these types of transformations here. If the change is taking place outside of the brackets, then it's what we expect in terms of f of x plus 3. We expect the y value to increase by 3. That is exactly what happens. It's being translated by the vector 0, 3, so it's moving up 3 spaces. Now, using everything we have done so far, please try to describe the transformation from y equals f of x to each of these functions. So for example, just say what is going on. Is it a translation? Are you moving up, down, left, right? Write the vector with which you are translating by as well. So yeah, pause this video, have a go answering these questions. I'll go through the answers in a sec. So here are the answers. So sometimes an exam question might ask you to determine the effect which a transformation has on a single point. So we're going to do this example together. The graph shows y equals f of x. The coordinates of the minimum point are given. Write down the coordinates of the minimum point of a curve with equation f of x take away 5. I would always sketch what this will look like. Don't try to do it in your head. Don't try to say, okay, look, x value here, -2. Let's just do -2 take away 5, and we'll get the answer and stuff. Like, don't rush. That's what I'm trying to say. We're going to have to move to the right. And now I know for sure that our x value will have to be it will have to increase by 5 units. So -2 plus 5 is 3, and I know the y value won't change, so it's going to be 3, 1. Sorry, y value won't change, so it's 3, -1. Here we have another example. So y equals f of x. The only minimum point of a curve is at point P. Write down the coordinates of the minimum point of a curve with equation. So very similar question to the one we did on the previous slide. I would sketch it. So the -2 is within the brackets. So I know we're going to have to move left or right. Because it's negative, we will have to move to the right 2 spaces. So it's going to look something like this. And our new minimum point will be 5, -4. Write down the coordinates of the minimum point of a curve with equation this. So two-part translation. Let's use orange. We're gonna x plus 5 within the bracket, so we're gonna move to the right. Sorry, we're gonna move to the left 5 spaces. So it's gonna be here, I think. It's probably not precise, but again, it's a sketch. It's not a perfect drawing. Here we're gonna have -2, so 3 take away 5, which is -2, -4. And then after we've done that, we have to add 6. So we have to increase by 6. So this is going to move up, increase the y value by 6. So this is going to move up, and it's going to be somewhere up here. And our new minimum point will be -2, -4 plus 6, which is normal to +2. So our new minimum point is -2, 2. Stretches have been removed from the main GCSE syllabus. However, you can just use the same rules as we've been using already. So if the value is outside of the brackets, then it's going to affect the y values. And so in this case, we are going to double our y value by 2, and we're not going to affect the x value. So x value is going to stay the same, 5 multiplied by 2. So our new coordinates are 3, 10. Now, one example for when the value is within the brackets. So f of 2x, when it's inside the brackets, the y value will stay the same. The x value will change. However, it's not going to be what we expect. We're not going to simply multiply by 2. We're going to have to do the opposite. So what is the opposite of multiplying by 2? Dividing by 2. So these coordinates become, as I said, the y value doesn't change. The x value, instead of multiplying by 2, we have to do the opposite, which is divide by 2. So 3 over 2 is our new x coordinate, which of course is 1.5. So 1.5 -4 is our new minimum point. Now, I talked about the stretches as an extension. I think if you're interested in studying A-level maths, then you're gonna have to do stretches within the A-level syllabus. So that's why I felt it was useful to mention it. Here, of course, we have everything you need to know for GCSE. So please make a note of it if you haven't done so already. I mean, I think you have made a note of some useful information already. But if not, then please make a note of everything on this table. And then we will move on and do some other examples. Moving on to reflections. So we have 2 questions on the screen. I'm going to use 2 different methods to answer these 2 questions. So we're going to draw the graph of y equals negative f of x and y equals negative g of x. So firstly, suppose that we have a function f of x plus 1. How could we draw the graph of y equals negative f of x? So Elise's method is to work out all the f of x values. So just by doing 5 multiplied by x plus 1, we work out the corresponding f of x values. Then she says that if I know the y coordinate for f of x, then all I need to do is change the sign for negative f of x. So I'll plot -1, 4. So essentially what she's saying is adding an extra row and changing this to 4, changing this to -1, changing the next one to -6, and so on and so forth. So now her x and y coordinates will be this and this, this and this, and so on and so forth. Of course, if you know all the coordinates, then you can plot these coordinates on a set of axes and you will have your graph of y equals negative f of x. So her method is based on her understanding of graphs as well as substitution and functions, understanding the relationship between these two functions. We're going to now look at a method which involves Elliott's understanding of transformations and specifically how to transform graphs. So how could we draw the graph of y equals negative g of x? So g of 1 is 2, negative g of 1 is negative 2. So that corresponds to here. G of 1 is 2, negative g of 1 is negative 2. So each of these, remember the x values are not changing, the y values are going to become negative. So this value up here, 4, becomes negative 4. Let's pick another one. This value here is a 3, it becomes negative 3. So the y values are changing, but if you look at the x values, they are still the same. So this is 1.5, I think, it stays the same. And remember, when the plus or minus sign or the operation is within the brackets, it affects the x values. If it is outside, and as you can see here, it's clearly outside, it affects the y coordinates only. The x values stay the same. So now I would like you to have a go at answering these questions. Pause the video and I'll go through the answers in a sec. For each example, reflect the graphs in the x-axis and give the equation of the reflected graph. So, reflect in the x-axis. So I'll draw the dotted line here. This is our line of reflection. And so this point will be here. These points will be right here roughly. It's a bit annoying, we have this red thing in the way, but our reflected curve will look roughly like this. And again, as you can see, the x values aren't changing at all. This x value is staying the same, the x value here is staying the same, but the y values are changing, and specifically the y values are becoming negative. So let's write the equation as well. So if f of x is x squared plus 1, then the reflection in the x-axis is going to be negative f of x. So negative x squared plus 1, which is negative x squared, take away 1. Now for the second one, let's draw a dotted line here. Again, same principle, just reflect it. So it goes something like this. Make sure it goes through this point. So like that. And again, if this is f of x, then negative f of x is just negative 2 to the x. So negative 2 to the x. Yeah. So remember, x values are not changing. The graph is being reflected in the x-axis, and the y values in this case are becoming negative. This y value here, which is a 1, becomes negative 1. This y value here is 2, and it becomes, okay, my drawing is not perfect, but it becomes negative 2, and so on and so forth. describe a reflection. So how could we describe a reflection in the y-axis? So now we're going to talk about reflections in the y-axis. So far we've only looked at reflections in the x-axis. Identify some coordinates and their reflections in the graphs below. So assuming that the green graph is our original, let's call it f of x. In the green graph, f of 1 is 2. So let's just highlight that here. When x equals 1, y is 2. F of 1 equals 2. Well, you can also see in the reflection, f of negative 1 equals 2 as well. So if the green graph has equation y equals f of x, what would the equation of a reflected graph be? So here we have y equals f of x. Well, let's look at the difference between these two. Well, this has a negative within the brackets. So I'll say this equation is also f of x, however there's a negative within the brackets, so it's f of negative x. So as you can see, the difference here is this negative 1. That looks really messy, but I hope you understand the principle. So yeah, this is f of negative x. As you can see, the y values aren't changing, the y values are not changing, but the x values are changing, and that's because when the negative is within the brackets, we are affecting the x values and keeping the y values the same. So here, coming back to this, rows of the table would make a lot more sense now, hopefully. But again, please let me know if you have any questions. Here I have a mini exercise for you guys to do. What effect will the following transformations have on these points? So I'll maybe do the first one for you guys. You could pause it right now and have a go yourself, but I'm going to do the first one for people just to understand how to answer these questions, I guess. So again, I think it's useful to, to be fair, you can't actually sketch these ones, but understand what is going on. So f of x plus 1 is within the brackets, so we need to move left. If we move left, that 4, 3 becomes 3, 3. That 1, 0 becomes 0, 0. The x value is changing, the y value is not. And that 6, negative 4 becomes 5, negative 4. For the next one, it's outside the brackets, so our y values will change. So yeah, have a go at answering that, and then do the others as well. And always think about whether you're going to change the x values or the y values. If you change the x values, y values stay the same. If you change the y values, x values will stay the same. So yeah, have a go at answering these questions now, and I'll display the answers in a sec. So I'm going to display the answers for you guys. Again, please let me know if you want me to explain some of these individually to you through email. As mentioned, there is a chance of there being a transformations question or two in our exam on Thursday, so please let me know if you require any help. So skill 2, sketching curves using transformations. So here is a sketch of y equals sine x. Now, no, it is the same shape as the one we looked at in our starter. However, because the axes are different, they go up to 4, that's why it looks a bit more squished, but it's not. It is the same as the one we looked at in the starter. On the graph, draw the curve with equation y equals sine x plus 2. So firstly, we can see the sketch of y equals sine x plus 2. Is it within the brackets or is it outside the brackets? If it was inside the brackets, it would be like this, but it's not. It's clearly outside the brackets, and it says it here. So we'll have to move our sine graph up by 2 spots. This is a 1, so it's going to end up here. This is going to be here. This is -1. So move up 2 spots to here, and the final sketch will look like this. So that's our, as you can see, x values are not changing, y values are increasing by 2. So here we have another example for you guys to do. You could pause this video, have a go answering it right now. If not, continue listening and I will do it with you guys. So sketch the graph of y equals sine x. On the same set of axes, sketch the graph of y equals sine x plus 30. The graphs below are each transformation of a curve. Okay, so that's question 2. So let's do it one by one. Remember, cos starts at 1, so sine starts at 0. This is 1 period. Go something like this. Could go on and on, but it's not very necessary. Let's just extend this. Okay, x plus 30 within the brackets, it's a plus, so we have to do the opposite of increasing by 30. We have to subtract by 30. So this is 180. This is 360. Okay, so this is not going to be the easiest sketch to do, so I'll just try my best, I guess. So everything's being shifted by 30 spaces to the left. With an orange marker, I'll just highlight a few points. So here, this is 330, this is 150, this is -30, and so on and so forth. Question 2, the graphs below are each transformations of the curve y equals cos x. Give an equation of each graph. So we know that y equals cos x starts at 1. So this, it looks as moved 180 spaces to the right. So, alright, y equals cos, it's moved to the right, so we're going to have the values within our brackets. So let's write x, move to the right, so it's -180, because it's moved 180 spots to the right. Now let's do the second one. As for the next one, it's perhaps a bit more difficult, but let's try to sketch a cosine graph. Just to understand where the points will actually go. So x goes something like this. Okay, it is fairly clear. We have shifted to the left by 60 x values. Yeah, fairly consistent across the board. So yeah, we can say that y equals cos x plus 60. Now, to test your understanding, have a go answering these two questions. Again, pause the video, I'll go through the answers in a sec. Here are the answers. So again, for the first one, we're changing our y values, keeping x values the same. For our second one, we are changing our x values, keeping the y values the same. Now, transforming, we've already talked about describing transformations, but we're going to look at another example here. The blue graph shows the line with equation y equals f of x. What is the equation of graph G in terms of f? So we could say that the graph is translated 5 units to the left, as you can see. This has affected the x values, so we do the change inside the function. So we do the change inside the function and do the opposite of adding 5. So we subtract 5, as in we move 5 spaces to the left, if that makes sense. I mean, we could just write translation and then write the actual vector. So negative 5, 0. We could write a little paragraph as they've done here. Or we could just write the function y equals f of x plus 5. And then it's really clear what transformation is taking place. Now we're going to link graph transformations to completing the square. So given that f of x equals x squared take away 6x plus 13, if we complete the square on that, we get f of x equals this. What does this tell us about the graph of y equals f of x in relation to y equals x squared? Okay, so we start off with y equals x squared, and then we work out the graph y equals x take away 3 squared, which is a translation in this direction. So the graph will look something like, I mean, I know the width isn't going to be great because I'm just sketching it, but the shape will look something like this. Then we need to add 4. So I'm going to y equals x take away 3 squared plus 4. And so we need to shift it up by 4 spaces, and I'll just use a different color. So, okay, which color is not there? I'll use black. So yeah, shift it up 4 spaces. So now we're changing the y value from 0, so this is 3, 0, to 4. So 3, 4, and look, that definitely corresponds to this graph, of this curve, I should say. But yeah, that's quite interesting for you to see the link between completing the square and graph transformations. So maybe have a go at answering these questions. Complete the square. It's a nice practice for you to practice completing the square, and then transform those. Start off with y equals x squared, of course, and using the functions in this form, work out where these four graphs will be located. So here we're going to look at one of them. I think it's the first one. Yeah, it's the first one. So start off with y equals x squared. Step 1, translate 4 units to the right. Because it's -4, we're going to shift to the right. So 4 units, so where is 3 and 6? This is 4, I'd say. Yeah, so something like this. There is our graph for x minus 4 squared. Step 2, translated 6 units down. So now I'll use a different color for this. Let's use green. 6 units down. So this coordinate here is 4, 0. It's now going to be 4, -6. And so that clearly corresponds with the purple graph you see. So the purple graph is the graph of this function, x take away 4, squared take away 6. So for your independent task, I would like you to complete at least 5 questions from the exercises slides. Please make sure you submit pictures of your work through the Teams assignment or by emailing me. So when I talk about the exercises slides, I am talking about the slides, the questions towards the end of these slides. So here's question 1, and it goes up to question 15, I believe. So we have a nice variety of questions. They start off relatively simple, they get harder and harder. And of course, if you click on this green box on each of these slides, you will be able to see the answers, so you can mark your work as well. Please make sure you mix it up a bit. Don't just go for the first few questions. Try to do 1 or 2 of the harder questions as well. To ensure you're getting a really good practice. So yeah, please make sure you answer at least 5 of these questions. And of course, submit pictures of your work. And after that, I'd like you to think about the homework tasks we have. So I'm hoping that all of you have finished your Maths Watch task by now. Sparks is due on Thursday, of course, and there are a lot of overdue tasks on Sparks. There are a lot of target tasks which haven't been completed, a lot of XP boost tasks which haven't been completed. But I guess for this week, your priority is preparing for this test, which will take place during our next lesson. We will do it through Microsoft Teams, through an assignment on Microsoft Teams. So please make sure you are on time, ready, and in the meantime, you could ask me questions as well for that test. I'll help you as much as I can in the next few days. So yeah, I hope you enjoyed and benefited from this lesson, and I will speak to you guys on Thursday, hopefully. Take care and stay safe.